Hey, Resin here. Welcome to part 8 of our Guitar Theory app series. Today we are expanding our scales functionality by implementing 5 essential patterns that make learning complete major and minor scales more intuitive. These patterns provide a systematic approach to mastering scales across the fretboard. You can find the complete source code in the GitHub repository linked in the description below. Instead of memorizing separate patterns for major and minor scales, we can leverage their relative relationship. This concept works because relative scales share identical note patterns but with roots positioned 3 semitones apart. For instance, C major and A minor contain the same notes, with A being 3 semitones below C. Our implementation determines the direction of this 3 semitone shift and applies modular arithmetic to ensure the resulting root note stays within our chromatic range, making scale navigation more efficient for guitarists learning to traverse the fretboard. To display this relative relationship in our interface, we implemented a component that accepts a relative root note probe. This component renders a clickable link that seamlessly navigates users to the corresponding relative scale. While we also utilize this component with pentatonic scales, the underlying calculation for determining the relative root note differs in that context. For those interested in exploring how pentatonic patterns work, check out our detailed explanation in the corresponding video linked in the description. To represent scales in our app, we use a scale type with 3 key properties. A type, either full, pentatonic or blues, a tonality, major or minor, and a root note. An integer from 0 to 11 representing positions in the chromatic scale. When a user selects a different scale, our app redirects them to a dedicated page for that selection. For those interested in exploring how scales are visualized on the fretboard, check out the first video in the series. You'll find the link in the description. Now let's examine the UI implementation that displays these patterns. Our scale patterns component creates a visual representation of the 5 pattern system, allowing guitarists to see how each pattern connects across the fretboard. The component dynamically generates patterns based on the currently selected scale using the getScalePattern function, which calculates note positions for each pattern index. Each scale has its own logic for calculating patterns. The getScalePattern function serves as a resolver that selects the appropriate calculation function based on scale type and applies it with the necessary parameters. Each pattern resolver function follows a consistent interface. It accepts both a scale object and a pattern index as inputs. The function processes these parameters and returns an array of note position objects that precisely map where notes should appear on the fretboard for that specific pattern. To represent the precise location of notes on the guitar fretboard, we define a note position type with 2 key properties, a 0-based string index and a fret number. The fret value uses a specific convention where -1 indicates an open string, no fingers pressed. 0 represents the first fret, and so on. Our scale patterns are built on the caged chord system framework, with each pattern anchored to a specific chord shape. The first pattern corresponds to the E form. While some note positions use fret index -2, not playable in open positions, we shift these patterns up to 12th fret area when needed for practical playability. This approach maintains the spatial relationship between patterns according to the caged sequence, allowing guitarists to smoothly connect all positions across the fretboard. For deeper understanding of the cage system that underpins these patterns, check out our detailed explanation in another video, also linked in the description. To implement this automatic octave shifting, our normalized fret positions utility detects patterns with fret values below -1 and transposes all notes by exactly 1 octave, 12 frets, preserving their relative relationship while making them physically playable on the guitar. For repositioning scale patterns across the fretboard, we implement the shift note positions function, which transposes all notes in a pattern by a specified fret offset. The getFullScalePattern function handles positioning scale patterns on the fretboard is a straightforward approach. For minor scales, it uses the relative tonality system to convert them to their equivalent major patterns. With the major scale, it retrieves a bass pattern, rotates the cage system distances to maintain proper spacing, and calculates an offset based on the root note, standard tuning, and distance from the first pattern. After shifting the notes by this offset, it ensures all positions are playable through normalization. This method creates a system where the 5 patterns connect naturally across the fretboard. The scale pattern component visualizes fretboard patterns by rendering note positions calculated by the getScalePattern function, leveraging the core fretboard visualization component introduced in the first video of this series to create an interactive representation of each scale shape. These 5 interconnected scale patterns based on the cage system will transform what was once a daunting memorization task into an intuitive learning journey. If you found this video helpful in understanding how to implement and visualize guitar scale patterns, please hit that like button and subscribe to the channel for more guitar theory and programming content. Drop a comment below if you have any questions about implementing these patterns in your own projects. Thanks for watching, and I'll see you in the next video.